next we will consider the similar thing that we have discussed till now, maybe isentropic flow to begin with, but through a variable area duct. So till now we have not taken area as a variable parameter, but now let us generalize the previous discussion somewhat and consider isentropic flow through a variable area duct. So when we say a variable area duct, maybe it is something like this, maybe it is something like this, we will not specify what it is, but the area of cross section will vary. So what are the basic equations that we may use here? One is of course the continuity equation, and we are all, in all cases we are assuming that it is a one dimensional flow. So rho into A into U, that is a constant. This is from the continuity equation. Then the fluid flow equation here, remember we are talking about an isentropic flow, so reversible and adiabatic. So it is having no friction, that means it is an inviscid flow. So what will be the governing equation for that? Euler equation, one dimensional form of the Euler equation. So Euler equation, so that is what, dP by rho plus u du equal to 0, that is the differential form of the Euler equation. Remember that in all cases of compressible flow that we are discussing, we are neglecting the changes in potential energy, the gravity effects are negligible as compared to the other effects. So this is like the, these are sort of like the fluid flow equation, and the thermodynamic constraint is the energy equation. So energy equation is like H plus u square by 2 equal to constant. But first of all we will not consider this energy equation as an important consideration, but we will concentrate on these two equations and see what we get out of that. So continuity equation, rho into A into U equal to constant. So what we will do is we will take log of both sides. So we will have ln rho plus ln A plus ln U is equal to ln constant, and then differentiate, that means d rho by rho plus dA by A plus du by U is equal to 0. Say this is equation number 1 and say this is equation number 2. Now if we want to relate this with the sonic speed, see in equation number 1 there is d rho, in equation number 2 there is dP. So somehow if we find out dP d rho, that will give c square. So we can relate this behavior with the sonic speed. So we can, so we write from 2 that dP is minus rho u du, and or if you want to relate it with u square, so dP by u square is minus rho u du by u square. So minus rho du by u. Why we have written in this form is because you have another form du by u in equation 1. So let us say this is 3, and from equation 1 you have d rho is equal to minus rho into dA by A plus du by u. So this is equation 4. So if you divide equation 2 by equation equation 3 by equation 4, you get dp d rho into 1 by u square is equal to du by u divided by dA by A plus du by u. If you consider it as an isentropic flow, dp d rho is c square. So, for an isentropic flow the left hand side is 1 by n square, because m is u by c. So, from here you can write dA by A plus du by u is equal to m square du by u, which means dA by A is equal to 1 minus or is equal to m square minus 1 into du by u. This is the relationship that governs the change in area with change in velocity, and it is one of the very important physical relationships which we have to carefully study. So, if you write say dA by A, so when you write dA by A, we think about two possibilities. See, I mean one of the possibilities is that along the direction of the flow the area is increasing or area is decreasing. So, this is an example with dA by A greater than 0, this is an example with dA by A less than 0, assuming that these to be the direction of flow. Okay. Now, if you consider m equal to 1 as a case, so m equal to 1 if you consider, then that will imply what? dA by A equal to 0, right. That means if you want to achieve m equal to 1, m equal to 1 is called as a sonic condition. In an isentropic flow it must conform to dA by A equal to 0. dA by A equal to 0, if you look into it mathematically, it may be either maximum area or minimum area, right. Physically we will see that it will conform to the minimum area. So, if you consider a possibility of these two types, say you consider this as a case, let us say that you have the inlet flow with a particular Mach number, whatever the Mach number at the inlet may be greater than 1 or may be less than 1. Now, we are interested to see the consequence. If you consider this particular geometry, if you see that no matter wherever m equal to 1 is achieved, we will see later on with a physical example that how m equal to 1 may be achieved. See, just think this geometry. So, this particular geometry, even if it is an incompressible flow, you see what is your target? The target could be to increase the velocity, that is why you reduce the area of cross section. So, these types of things where you have a variable cross sectional area with an intention of increasing the velocity, and therefore the consequence is reduction of pressure, that is known as a nozzle. So, if you have a nozzle, your target is to have an increase in velocity, but just this geometry does not ensure that it will be like that for a compressible flow. For an incompressible flow, area reduction will imply that the velocity will increase. For a compressible flow, if you think it like that, it may be wrong, because rho is also another factor, it is rho into A into V, not just A into V. So, rho may vary in such a way that it might be that if area is increasing, velocity is also increasing. So, it all depends on the Mach number at which the fluid is there. So, we will see later on that what is the physical implication of this minimum area when we discuss more about the nozzles, the converging nozzle, this is called as the converging nozzle and the converging diverging nozzle. But look it in the other way, if m is not equal to 1, then can you have dA by A equal to 0? Definitely if m is not equal to 1, then you may have dA by A equal to 0 if du by u equal to 0, that means u is either a minimum or a maximum. So from this we come to a very important conclusion that if for the time being we take that at the minimum area m equal to 1 is achieved, that does not mean that at the minimum area m equal to 1 is always achieved. It means that if m equal to 1 is achieved, somewhere it has to be a minimum area location, but the minimum area location will not always have m equal to 1. If it does not have m equal to 1, it will have either a minima in m or a maxima in m, and we will see that how it is possible. To understand that, what we will do is we will consider two different cases, one is m greater than 1, another is m less than 1. So if you consider m greater than 1, so if you consider m greater than 1, you can see that if you have a reduction in A, that means if dA by A is reducing, then du by u that is also reducing, right. That means if area decreases, the velocity also decreases if the flow is supersonic. This is non-intuitive. Incompressible flow consideration will say if area increases, the velocity will decrease. So why it happens? Roughly if you see that what you are keeping fixed, rho into A into u, so you are reducing A, you are expecting u to increase, but with a reduction in A, maybe there is such a high increase in density that there is actually a significant reduction in u to keep the product as constant, okay. So that is what is happening here physically. So what we get out of this is when m greater than 1, that means if you have dA by A, that is if area is reducing, then the velocity is reducing, therefore it is not acting like a nozzle. It looks like a nozzle, but it is acting like a diffuser. Diffuser is something where you want a decrease in velocity and an increase in pressure. So here it is acting like a diffuser. So physically looking like a nozzle does not mean that it is a nozzle. One has to see what is the Mach number range in which it is operating. On the other hand, if m is less than 1, you have dA by A will be, if it decreases, that will mean that du by u is positive, that means u increases, right. So if this situation we may intuitively think as physically analogous to an incompressible flow behavior in a nozzle only if Mach number is less than 1, only if it is a subsonic flow. If it is a supersonic flow, that is not the case. So if it is a subsonic flow, what happens? If it is a subsonic flow, so now think about such an arrangement. So this is an arrangement where the area is reducing, it comes to a minimum and then increases. So in this kind of an arrangement, if you see, if you plot, so let us say that the arrangement is like this, we plot the Mach number versus x. For two cases, assuming isentropic flow, for two cases, one is the entry Mach number greater than 1, another is entry Mach number less than 1. So if the inlet Mach number is less than 1, say the inlet Mach number is less than 1, say this is Mach number equal to 1, say inlet Mach number is half, like this. So as you go through the converging section, the velocity will increase and therefore the Mach number will increase. So the Mach number will increase and it will come to a maximum when dA by A is 0, okay. So it may not achieve 1, but it will come to a maximum and then it will fall because the area variation is different. On the other hand, if the inlet Mach number is greater than 1, then the velocity will reduce in the converging section and therefore the Mach number will reduce. It will come to a minimum therefore here and then will increase again. So if the entry is supersonic, the throat may have a minimum Mach number. If the entry is subsonic, the throat may have a maximum Mach number, but these are limited by Mach number equal to 1. So if it is supersonic, it is remaining supersonic for all the locations. It is coming only to a minimum here, but that is still greater than 1. On the other hand, if it is subsonic, it is remaining subsonic everywhere. At the throat it is coming to a maximum, but still less than Mach number 1. So from this we conclude a very important thing. It is not necessary that at the throat, this location of minimum area is called as the throat, that at the location of the minimum area it is not necessary that we will always have Mach number equal to 1, but the converse is true. If we have at some location the Mach number equal to 1, that must be at the throat, okay. Again remember, there are very important assumptions associated with it. The assumption is it is an isentropic flow. So if it is a flow with friction and flow with heat transfer, then the location of this sonic point Mach number equal to 1 shifts. It is no more at the throat, it is at either the upstream or the downstream depending on the heat transfer in the flow and friction in the flow, okay. Now it is also possible to write this expression of dA by A exclusively in terms of dm by m. So let us try to do that, because it will give an exclusive variation of or exclusive relationship between Mach number and the area. So let us write say d. So we know that the Mach number is equal to the C into U. We are interested to express du by u in some way in terms of dm by m, so that we write dA by A explicitly in terms of dm by m. Sorry, u equal to C into m, right. Now what you may do is you may take log of both sides and then differentiate. See, for all these cases, by this time you have realized that there is a purpose in taking the log and differentiating, because you are getting this type of expression dA by A, du by u like this by taking log and differentiating. There are other ways of getting it, but this is the easiest way of getting such forms. So log of u equal to log of C plus log of m, and then you differentiate. So you will get du by u is equal to dC by C plus dm by m. So in an effort of expressing du by u in terms of dm by m, we have come up with a new unknown dC by C, but C may be expressed in terms of the temperature. So let us give this equation some numbers. Let us say this is equation number 5 and say this is equation number 6. Now we know that for an isentropic flow, see, we are writing all these equations for isentropic flows. So C is equal to root over gamma RT for isentropic flow. So again we take log, so log C is equal to half log gamma plus half log R plus half log T, that means dC by C is equal to half of dt by T. So, dC by C is half of dt by t, therefore, you can write from 6 that du by u is equal to half dt by t plus dm by m. Again another new unknown dt by t has appeared, but till now we have not used the energy equation, that we may use. So, energy equation what it was, H plus u square by 2 equal to constant, that was the energy equation. So, you have dH plus u du equal to 0. And for a perfect gas this is Cp dt plus u du equal to 0. In place of Cp we can write gamma r by gamma minus 1. If you want to write it in terms of du by u, just divide both the terms by u square. And u square is equal to m square into gamma RT. So, this is m square gamma RT. So, gamma r gets cancelled. So, 1 by gamma minus 1 m square dt by t plus du by u equal to 0. So, we have been successful in writing dt by t in terms of du by u. So, from this we get dt by t is equal to minus of gamma minus 1 m square into du by u. So, this is 9. So, if you combine 8 and 9, this is du by u, dt by t is written in terms of this, half of this is half of the right hand side, and so that will become 1 plus gamma minus 1 by 2 m square du by u is equal to dm by m, right. So, that we may substitute in equation number 5 which is there to get dA by A is equal to m square minus 1 into in place of du by u we may write dm by m So, from this equation we may get an explicit relationship between the area and the Mach number. So, if you know how area varies with x, you can easily get how the Mach number varies with x. So, for a given geometry A as a function of x, you will get an output as a Mach number as a function of x, and from here you can clearly verify the statement that we have just made. So, if m is greater than 1, see the denominator is always positive because gamma is Cp by Cv, Cp is greater than Cv always. So, this is positive, m square is positive, so denominator is positive, so numerator is dictating the sign. So, if m is greater than 1, dA by A positive means dm by m positive, and if m is less than 1, dA by A negative means dm by m positive. Okay. So, whatever statements we made in terms of du by u, similar logic holds for dm by m, and hence these plots you can verify the natures of these plots. Okay. Now, the other consideration regarding these types of flows is the achievement of a sonic condition. So, we have given some emphasis on that, and we have seen that if the sonic condition at all has to be achieved, that is achieved at a location where dA by A is equal to 0. Although at dA by A equal to 0 sonic condition need not necessarily be achieved, but if it is achieved at all, it is achieved there. Now when the sonic condition is achieved, these sonic states, this is usually given by a quantity star in the description of the flow. So this is just a symbolic way of representing. So if at a state sonic condition is achieved, let us say the corresponding velocity is u, we call it u star, the corresponding pressure is P, we call it as P star, corresponding density as rho star, corresponding area as A star, like that. These start quantities are important because these are some important reference quantities. Remember that there may be cases when no sonic condition is achieved at all. Look at these examples, either the top curve or the bottom curve, sonic condition is achieved nowhere in the flow. So still u star, rho star, P star, rho star, A star, these quantities exist because these are hypothetical reference conditions. For example, A star is what? A star is at a given condition what could be an area at which a sonic condition would have been achieved, not that that area is physically there in the flow. So for corresponding to each state there is a corresponding start quantity, and if you see tables of properties of compressible flows, these start properties are there. So these are very important reference quantities, not that these values have to exist in the particular flow condition, but these are reference quantities with respect to which other quantities may be expressed. For example, if you have say a condition where this sonic state is achieved, then you may write rho AV or say rho AU is equal to rho star A star U star. Okay. So this is a hypothetical condition. If the sonic state is achieved, it may be achieved in reality, may not be achieved in reality, but if it were achieved then still it should satisfy the mass conservation. Okay. So you may write as A by A star as rho star by rho into U star by U. Remember that U is equal to m into square root of gamma RT, right, for an isentropic flow. When it is U star, it is square root of gamma RT star, because m star equal to 1, star condition is sonic condition. So when you write star, that means the Mach number at that state is 1. Okay. So this may be written as rho star by rho into U star by U is root over T star by T into 1 by m, right. How you can write T star by T? We may use the stagnation properties and we may use the reference with respect to the stagnation properties. Remember we had T0 by T is equal to 1 plus gamma minus 1 by 2 m square. We just now derived this. If it is a stagnation property, remember that when it is an isentropic flow the stagnation property does not change. Why? For example, the stagnation temperature does not change for an isentropic flow. Why it does not change for an isentropic flow? See, consider the energy equation, H plus U square by 2, this is a constant and this is equal to H0. So whatever may be, if H varies, U also varies in such a way that sum of these is equal to a constant, and therefore H0 is a constant. H is like Cp into T for a perfect gas, and that is why T0 remains a constant. In fact, it is not necessary that it has to be isentropic. Just for adiabatic flow T0 is a constant, because reversible condition is never used here. But when you use this relationship, it uses the isentropic condition also, because it uses P by rho to the power gamma equal to constant for the sonic speed derivation, from which this expression comes. So T0 equal to constant, that means you can write T0 by T star as what? What is T0 by T star? 1 plus gamma minus 1 by 2, that is gamma plus 1 by 2. So you can write T star by T by dividing these two expressions. So T star by T is 1 plus gamma minus 1 by 2 m square by gamma plus 1 by 2, right. Also we know that T by rho to the power gamma minus 1 is equal to constant for an isentropic flow. So you can write T by rho to the power gamma minus 1 is equal to T star by rho star to the power gamma minus 1. So rho star by rho is equal to T star by T to the power 1 by gamma minus 1. So A by A star So, you have T star by T to the power 1 by gamma minus 1 into T star by T to the power half. So, T star by T to the power half plus gamma minus 1. So, half plus 1 by gamma minus 1. So, gamma plus 1 by gamma minus 1, right. So, this is T star by T to the power of gamma plus 1 by gamma minus 1 1 by m, right. That means you have A by A star sorry 1/2 is there to the power gamma plus 1 by 2 into gamma minus 1 this into 1 by m, right. So, what it tells is that given a value of m you can get one A by A star. Looking from the other angle, given one A by A star you could have some value of m, but it is not a unique value of m. You could have multiple values of m. That is very clear from this because it is an equation having multiple roots. So, it will have basically two acceptable values of m, and if you look into the tables of properties of compressible flows, usually these quantities are referenced. So, you have for each Mach number certain important properties are given. So, if you look into isentropic flow tables, which in the next class we will look more carefully. So, if you have the isentropic flow important properties, what are the important properties? So, for each Mach number you can have P by P0, T by T0, rho by rho 0 and A by A star. It is important to tabulate this because if you know the Mach number you can calculate all others, but if it is a reverse problem, that is if you know A by A star, calculate what is the Mach number, all those multiple roots you may have to solve nonlinear equations, but if you have a tabulated set of data you can just read from the table, and that is why the compressible flow tables are there with every book in the chapters of compressible flows, the corresponding there will be an appendix where these properties are there. So, these properties will relate everything with a reference star, the reference is either the stagnation state or the sonic. Important thing is that the stagnation state is the same so long as it is isentropic flow. If the isentropic nature of the flow is disturbed, then the stagnation property changes. That means T0 is same so long as it is isentropic, but if the isentropic nature is changed, if it is no more isentropic, then the stagnation properties change. And one of the important mechanisms that can create such abrupt change in stagnation property is a shock, is the presence of a shock wave. So in our next class we will see that how these properties get changed when you have an abrupt discontinuity in a compressible flow medium present in the form of a shock wave. So that we will take up in the next class. Thank you.